Hello and welcome to our program, Astronomy for Everyone. The topic for this month's program is how to mount your cell phone on a telescope. And here to show us how to do that is John McGill. John, welcome to the program.
Hi, Don.
Good to have you back again on this side of the camera. Before we get started, tell our viewers about your t-shirt.
Oh yeah, that's the Great Lakes Stargaze. That's going to be coming up in October. So that's going to be next month. And it's October 3rd through the 6th. And that will be up in Gladwin, Michigan. And what a great time we have up there. Those are such dark skies up there. I mean, the stars look like they're blue. It's just, you can see the Milky Way. And it's a great time. And this is an astronomer's star party. So you can go up there and you can set your telescope up, and you really don't have the general public up there. And it really is a great time.
Yeah, it is. I've been up there several times myself, and it's really just a good atmosphere to be around all these, junior or amateur astronomers and imagers, and it's a great time.
It is.
So we're going to be showing folks how they can take some really good images using their own cell phone. So let's get into it.
Yeah, so probably most of you all have cell phones, and I'm sure that you've tried taking pictures of the night sky. And after you find out what your cell phone is good at, you're mostly taking wide-angle shots of the Milky Way. But then now you've taken enough of those shots, you want to start getting into more, say, planets or deep sky objects. And so to do that, you basically, you're limited by your camera. And your camera has a zoom, an optical zoom, that can possibly go up to 5 times. But most of your cell phones that have one camera, it's basically a 1-to-1, so it's basically what your eye sees is what your camera sees. And you do have our digital zoom, but digital zoom, when you start going digital zoom, that starts to make, it takes the amount of pixels you have. Think of a piece of graph paper, and a graph paper has so many squares. Just say you have 100 squares on a piece of graph paper. Now if you come in off the edge of the graph paper 1 inch all the way around, and then you cut those off, that's what your digital zoom is it's cutting off so many of the pixels. So you're actually eliminating data when you digitally zoom. So to get past that, you want to do what's called eyepiece projection. And that's where we take the cell phone and we mount it to an eyepiece, and then we put it on the telescope, and we actually use the telescope to be the lens of your eyepiece. So let's see if we can show you a little bit of that.
Yeah, that'll be interesting, because I think people really want to do more, like you say, shots of the Milky Way or maybe the moon.
Yeah.
But this would also help with shots of the moon as well.
Oh, definitely. And with your cell phone, you can also use it to video record the moon, and that's what we call lucky imaging. And then you take the video and then you put it through different software, and that extracts individual images from your video, but it only uses the best. And so that's how you can get really clear, sharp pictures of the moon.
Yeah, especially with problems of the atmosphere and the wiggle from warm air currents and unsteady looking images.
That's the other thing I wanted to talk about is magnification. Magnification, if you look at these numbers on the front of the telescope, you can see there's a D and it says 2032. Well, that's the diameter of the telescope. So this translates to about 8 inch. So this is called an 8-inch telescope. And then you have this capital F number, which is 2035 or 32. And that number is the distance that light travels through the telescope, and that's the focal distance. And so it goes back and forth in this one because this has mirrors. Then it comes out the eyepiece in the back here. And so these numbers then, if you take the large number and you divide it by the small number, then you get your F number, which is F10. So basically, roughly, we can call this, the diameter is 200 and the focal distance is 2,000. So this is the important number right here, this 2,000, the focal distance. So now if we take the focal distance, say that's 2,000, and then we have eyepieces. Eyepieces are numbered in millimeters, so this one's a 14 millimeter. So a 14 millimeter, if you take that number 2,000 and you divide it by 14, that comes up with 143 times magnification. So getting back to your cell phone, you're dealing with about 5 times magnification. So you can see what the benefits of using your telescope and your eyepiece.
Exactly.
Okay, now let's go back. I'll set this over here. Okay, now this is the tridapter. This is one of the better brackets that's made for mounting your camera to your eyepiece. And the reason why I say it's one of the better ones, when we open the box, it has a nice little bag on it. And we can take it out here. You can see this is made, it's all metal.
Oh, yeah.
Some of the original ones were plastic. And it has metal knobs on it even. And they call it a tridapter because it moves on 3 different axes. It has the X, Y, and Z axis. So let me show you basically what we want to do with this. Is we want to open this one up.
So that allows you, opening that up, to be able to put that eyepiece in there.
Yes, and this is a large eyepiece. You can
2-inch, I believe?
It's not a 2-inch. It looks like it by the size of it because it's a wide field of view. But this part is the 1.25 inch.
Okay, 1.25 inch.
Not a 2-inch.
Okay.
It will take standard 2-inch eyepieces. I do have a 35 millimeter panoptic, and that one is too large. But I have a 32 millimeter Meade Plazelle, and that one will fit.
Oh, okay.
So this is about the largest bracket that you can get for it. So now we have our eyepiece in, and now we're going to put our phone in here. And so we want to have it so that this plane that the phone's going to be on is right about on top of here. So this looks like it's got to go up just a little bit. So we move this bottom one and we take that up a little bit. And it's a little bit high.
Well, this is nice. Once you get the eyepiece set in its holder, you don't have to keep trying to make micro adjustments with the eyepiece. You can adjust it off the bracket.
Just with the bracket, yes. And this has 5 knobs on it. 3 of them are your 3-axis, and those knobs are different size than the ones that are just to hold things in place.
It's good for nighttime. You can use the eyeballs in your fingertips.
Yes. Okay, so now that we have the eyepiece in the bracket, now we're going to want to take it in. Our camera lens is over here, so we're going to try to get this in here first. We're going to want to open this up, and this will take most size cameras or cell phones, large ones or small ones.
It looks like it's fitting in there quite nicely.
So we want to tighten it up pretty good. Okay, so now we got it tightened up, but if you can see, there's a little bit of a gap.
Yeah.
So let's bring that back down and see, we bring the phone down on it. And by doing this, it takes a little strain and it kind of supports the cell phone a little bit better.
Okay.
And also that helps if you have to take this bracket off once the eyepiece is back in the telescope, you know, to focus if you move onto a different object.
Okay.
Because you want to look through the eyepiece to get it the best, and then you put this back on.
Sure. I noticed the eye relief is down. Do you want the eye relief down on the eyepiece?
Yes, and what Don's talking about, eye relief, is
the little rubber cup, yeah. Mm-hmm.
And the reason I put it down is so that it's a better support.
Ah, okay.
You know, basically 1, 2, 3 point.
Good idea.
Okay, now we're going to take the cell phone and use the camera on the cell phone to try to get it focused and centered. And now you can see that it's pretty close to being centered if you take the curvature on the top and the bottom. So once we get to that point, then we go ahead and we just drop it in. And if we had this out in the night sky, this would be all set up. And then one other thing that's in the box is it comes with a trigger, a Bluetooth trigger. So with that, you don't have to touch the cell phone and get it to, you know, wiggle or make it blur.
Right. In the old days with the old film cameras, we used to have the little cable with the plunger.
But to me, the only time I would use this trigger is if I was taking a video. But if I'm just taking pictures, I would set it to like a 3-second delay. And
Okay.
that way you hit it and then it calms down before the 3 seconds are up.
Another way to do it. Yeah. So this is quite a nice setup. And I can see we got a good shot of it right there. And this is really an amazing gadget. It's a whole lot better than just trying to hold your cell phone over the eyepiece.
And here's something else you can do with this too, Don, is like what we were doing here. This was actually, we were on a Zoom call, and that's how we were bringing you what's in the camera. And so by doing a Zoom call, you can invite your friends and invite them to your night out of observing.
Terrific. A great idea. Well, we're going to take a quick break. If you have a question, please send us an email. The address is down at the bottom of your screen. And coming up next is Term of the Month with Stephen.
Thanks, Don. The term of the month is Hubble tension. Hubble tension is the difference found when determining the Hubble constant via distance by standard candles versus via cosmic microwave background radiation. A new study of 11 galaxies using the James Webb Space Telescope shows error bars for the two overlap, so there's no tension. It should be noted that there has been tension. This tension has been something of a work in progress for the last 10 years. While there are astronomers who find the new JWST work convincing, a published critique points out that there's a small sample size, that is 11. Everyone agrees that more work needs to be done. The Hubble constant is a measure of the current expansion rate of the universe. The standard candles method involves objects of known brightness. These include Cepheid variables as well as red giant stars. They could also include Type 1a supernovae. The brightness observed gives you a distance to the object. The apparent brightness of the object is compared to the redshift of a containing galaxy. The redshift can be converted to a distance from us. Issues that occur include accounting for red light absorbed by dust. but also stars are often near other stars and could make the star appear brighter than it really is. Bigger telescopes allow better brightness determination, so the James Webb Space Telescope has a 4x advantage over the Hubble Space Telescope. Meanwhile, the cosmic microwave background radiation can be used to measure the Hubble constant at the start of the universe. Using models, this is converted to a modern Hubble constant value. The rate of expansion changes over the age of the universe. The Hubble constant is only a constant at any given age of the universe. No matter how you attempt to measure the Hubble constant, it's a messy business and progress is difficult. Even in this case, where measurements are attempted, science should be viewed as a process for getting at the truth rather than any particular number, like 73 kilometers per second per megaparsec versus 67.4 kilometers per second per megaparsec, a difference of 8%. Hubble's own estimate was 600% off. And that is the term of the month, Hubble tension. Back to you, Don.
Thanks, Stephen. We're back here with our guest, John McGill, who's been talking to us about how to use your cell phone with a telescope. Now, is there another reason why someone would want to mount their cell phone to a telescope, John?
Yeah, and this one doesn't have to do with taking pictures, but it has to do with using your cell phone as a navigation tool. And by doing that, some people may have heard of, I think it's Celestron has a program called StarSense, where it uses cameras or your cell phone, and it plate solves. And what plate solving is it takes a picture of the sky in where your camera is pointing, and then it tells you exactly where it's at by matching basically a catalog of stars to what it's seeing.
Exactly.
And what it does is it guides you, because once it knows where it's at, then you punch in where you want to go, and then you move the scope manually, but it tells you, and they call that push to, where this is normally a go-to, meaning it's fully computerized. But say you have a Dobsonian telescope. Most Dobs, those are the ones that have the mount on the ground, and they're a big tube. And people buy those because it's the best bang for the dollar for aperture. And most of those didn't have any kind of navigation system. And so with this program, you can use it and convert, your totally manual into a push to. And the reason why I'm putting it on this one is because these Meade telescopes, these first came out in the 1990s. And I don't know, some of you may know that I repair the Meade telescopes, but some people don't want to fix their telescopes because they may have gotten it from a relative and it doesn't work anymore, but they still want to use it. And so this can modernize it where you can still use it if you don't know what the real sky is. A lot of amateur astronomers, even in the city, you can only see a few stars, and you don't see whole constellations, so you really don't know what stars. It
makes it very difficult because of light pollution.
So this way it helps you through it. So with this, this is a 3D bracket. You can find this on the internet. The program that I'm going to be using, it's called Astro Hopper, and this is a bracket, but you can make something similar to this if you use just a sheet of like Luan or real thin plywood and put some push pins or thumbtacks in it, and then maybe instead of this side you could use like a quarter round molding, and just make something simple. Or even if you had a sturdy box and you just cut it out and
sure,
use your imagination. Some people would take their piggyback bracket for their camera and then just put a normal cell phone bracket on there, and they can use that screw and hold it on that way.
Exactly.
So you just have to be creative, but this was an easy one, and it got me to use my 3D printer. So this just goes on the top here. And these are just rubber bands, and if you don't have a long enough rubber band, you can just daisy chain them together, you know, link and lock.
Okay. Or maybe if you got some zip ties.
You could, but a zip tie, that's more permanent. You know.
That's true. Yeah, rubber band you can just take off.
Yeah, and some people, they use Velcro, but then you're going to put Velcro on the back of your camera too, and so I don't go for that. But you could even just use rubber bands without any bracket. But anyways.
But this gives you a nice flat platform.
Yes.
To put the phone onto.
So here, get this rubber band up here. There we go. Okay, now we got it mounted to our telescope. And so, as I said, the program that we're using, it's called Astro Hopper. And the first thing is this message, a quick start guide, so you can go through that on your own, but we'll just go past that. And now it says enable device orientation, so we click that, yes. Allow, yes. And now what we have to do is we have to align it. So now I'm pointing this north, so let's point it in, we all can pretty much see Polaris. So yes. We'll pick Polaris as our alignment star. So we'll say there and then align. And so then we push it. I'm going to loosen up the clutch on here a little bit. And as you can see, we go right there and we're aligned.
Okay, you had that little greenish blue circle?
Yep. So now let's move this over and say, or we can go over here and let's hit search. And so search, let's hit, say we want to go to M51. M51 is the Whirlpool Galaxy.
Exactly, right in the neighborhood there of the dippers.
Okay, so now we hit that and we say search, and that tells us where we want to go now. So here, let me take this part out, and you can see we're going down, or actually going up, but this is backwards. And there, then that should be right in our eyepiece.
Terrific. As I say, the hopper is a great word because you're basically star hopping, which is what experienced astronomers know how to do.
Oh yeah, we used this bracket right here on the side of the telescope is for a telrad, and that had the setting circles on it.
Exactly, I remember using those, sure.
And that, we used to use that with our charts, and that's how we used to star hop.
Yep, just use that, and the bigger circle, then the medium circle, and the inner circle. So this is really, as you mentioned, you can take the most basic of telescopes and make it almost a go-to, but you're pushing it yourself.
Yeah, this reminds me a lot. I was a boater, and we used to have the type of navigation, it was radio navigation. That was before we had GPS, and that was basically the same way. It would give you the arrows, and it'd tell you need to take the boat that way, but same type.
John, this has been fantastic. I don't know who doesn't have a cell phone these days, but if anyone has really any interest in the night sky, either taking pictures or just finding objects to look at, this is really the way to go. So thank you for being here to tell our viewers all about this. Please visit our club website. The address, as always, is down there at the bottom of your screen. And coming up next with What's Up in the Night Sky is Stephen.
Thanks, Don. What's up in the night sky for September 2024? The days change night and day lengths fastest this month through the equinox and slowest on reaching the next solstice. The autumnal or spring equinox is September 22nd. Mercury and Venus are near the Sun all month. September starts with a new moon on the 2nd, first quarter on the 11th, full moon on the 17th, and third quarter on the 24th. Shown here on the 30th of December is Venus. Venus goes from Virgo to Libra and sets about an hour after sunset. Then we show Mercury on the 1st of September. Mercury goes from Leo to Virgo. That's Virgo again, right? Mercury rises about an hour before sunrise to, at the end of the month on the 30th, we have superior conjunction. Superior conjunction is when Mercury is going behind the Sun. We won't be seeing Mercury. So Mercury is obviously best at the beginning of the month. Some other numbers for Mercury. Max western elongation is September 4th. That is when Mercury appears to be farthest from the Sun in the sky. And perihelion on September 9th, that's when Mercury is physically closest to the Sun. Then back on September 30th, we have the all-month lineup near midnight. Now, remember that when we looked at Mercury just now, we saw Mars also at the top of the screen. So we could get Mars and Mercury easily on a screen, but I couldn't get Mercury and everything else on the screen. So Mars goes from Taurus to Gemini, rises 4 hours before sunrise to about 6 hours before sunrise. Jupiter is in Taurus and also does that. And Uranus is also in Taurus and also sunrise 4 hours before sunrise to 6 hours before sunrise. Neptune is in Pisces, and it has opposition September 20th, so it'll be up all night pretty much. Saturn is in Aquarius, and it has opposition September 8th, so it'll be up essentially all night. Pluto is in Capricornus and sets from about 2 hours before sunrise to 4 hours before sunrise. And that is what it's up in the night sky for September 2024. Remember, we don't charge money for this show, but we may tax your brain.